Great. Hi, everyone. Thank you for having me. My name is Kenneth, and I'll be presenting my paper, Virtually Physical Immaterial, an appraisal of augmented reality in architecture. So I'll be going through the paper, which is broken down in a few sections. There will be an introduction, a background review, followed by the HCI experiments, implications, and conclusion at the end. So a little bit about myself. I went to the Bartlett School of Architecture, UCL, and research as part of my thesis for my master's degree in architecture in Bartlett. And these are some of my design work, exploring the intangible realm in between physical and digital, computer vision and surveillance. And the research paper goes parallel with the design work that I've done. Software is eating the world. In the future, imagine being able to change materials and colors of walls and floors in your home in an instant, substituting your television, computer with virtual screens, and virtually rearranging your furniture just with a few gestures of your hand, all visualized through a pair of smart glasses. Currently, there's a fundamental disconnect between the massive wealth of information in the digital world and the physical world in which we apply it. However, AR promises to bridge that gap by superimposing the digital onto the physical. Mass deployment of immersive technologies is agreed by most to be inevitable. A future where architecture contains augmented components is a future that is more than possible and worth discussing. Although much has been articulated in how we can use AR in architecture, little research has been done in how we respond to AR and ultimately how we will value and how we should use AR in architecture. As architects are trained to design and imagine 3D spaces, it is only natural for us to think about the following question. How can and should architects leverage AR as a new form of spatial conception? And consequently, how can this impact architecture programmatically and cognitively? This research investigates the potential benefits and drawbacks of AR in architecture and how it can transform architecture's spatial properties and performance. So to begin, we must first understand what AR is and where it sits in relation to other immersive technologies, namely virtual reality or VR. AR is a crucial but often overlooked by architects relative to VR. While VR surrounds the senses and immerses the user in a completely synthetic world, which may or may not mimic the properties of a real-world environment, AR presents information additional to the real surroundings. Most commonly, AR is defined as belonging to a narrow class of display systems comprising of some kind of handheld device, HHD, head-up display or HUD, or head-mounted display, HMD. In these cases, the viewer observes a direct see-through view of the real world, either optically or via video coupling, on which the computer-generated graphics are superimposed. The device used to perceive AR contributes as one of the main factors for level of immersion, from HHD to HUD to HMD as the most immersive as of now. But what is immersion? VR takes advantage of the imaginative ability of people to psychologically transport their presence to another place. The sense of presence, or SOP, is therefore a term often used to measure the immersive potential of a system. And break in presence, or BIP, is a moment during a virtual experience in which the user becomes aware of the real-world setting. Many might believe that the SOP does not apply to augmented reality, as the user can see the real world, but the sense of presence in AR should refer to the presence of virtual objects instead, with users feeling that they are with the objects. As such, if the breaking presence in VR is a moment that a user's own presence is disrupted, the breaking presence in AR is a moment that the virtual object's presence is disrupted. And so the notion of VR as a more immersive technology than AR is misleading and often resulted in AR as an overlooked tool in the architectural discipline. Isolated AR applications have been around for decades, but only recently have the technologies required to unleash AR's potential become available. This includes the holistic development in software, namely computer graphics, from wireframe to shaders to real-time rendering, hardware from heavy devices to lightweight smartphones to speculations of a new generation of smart glasses, and infrastructure with BIM and digital twin on the rise, and with concept of AR cloud and mirror world. Currently, AR is no longer solely isolated applications, but the same augmentations can be viewed by multiple people at the same time. In the duration of the period of the mentioned technological development, humans have pretty much stayed the same. And to understand how we behave and react using AR, we must also understand how humans process visual information. There's reality and reality that we perceive. Most relevant to AR, our perception of surroundings does not necessarily represent physical reality. All sensorial experiences we have are receptive and come to us as electrical pulses. Our brains interpret these electrical pulses to create a highly elaborate simulation of reality. And as humans, we rely heavily on visual cues for basic adaptive and complex behaviors, making thousands of conscious decisions every second while interpreting spaces. Excuse me. The two visual systems hypotheses proposes that the ventral stream, or the what pathway, plays the major role in the perceptual and identification of objects, while the dorsal stream, or the where pathway, translates visual information for motor planning and spatial navigation. So if our understanding of reality relies on our sensory inputs and we can manipulate our visual inputs through AR, how can it affect our understanding of our surroundings? While we understand that AR cannot change the physical properties of objects, the HCI experiments investigate how alterations of visual perception changes our understanding of reality through AR. With the hypothesis modifying our visual perception with AR, our understanding of our surroundings can be altered. And sub-hypotheses, virtual materials can substitute physical materials, and virtual objects can exert physical influence. So two complementary experiments were conducted. Each experiment has slightly different objective while covering similar ground. targeting the two different visual streams in our cerebral cortex. Experiment 1, or E1, was an object augmentation, changing the materials on the object to observe human abilities in object recognition in AR. And experiment 2 was a spatial augmentation, placing virtual objects in a space to observe human behavioral change during spatial navigation with these objects present in AR. A white 3D printed Utah teapot was used as the target object, as it is a benchmark object that is relatable to most people and not immediately recognized as fictional or digital. A handheld webcam was used to capture the target object and display on a computer screen. Participants were asked to observe the object on the computer screen, and a total of 3 versions of the object, 01 to 3, were shown. 01 with an augmented material was shown first, then 02 with no augmentation, and then 03 with another augmented material. This allows the observation of response changes from augmentation to no augmentation and vice versa. A list of questions was asked during the session alongside the AR experience. So here you can see the process of the development of E1, as well as some photographs taken during the session. On the right, you can see the 3 objects participants had to observe and describe during the session. For the spatial augmentation of E2, a linear corridor space was chosen as a corridor is navigated in a singular linear direction. This minimizes confounding variables associated with individuals' preferences in spatial navigation. Participants were asked to navigate space using a designated iPhone's display as their only viewpoint, and perform 2 separate walkthroughs of the hallway, first without augmentation as control, and second with augmentations as test. Participants' movements were recorded and mapped afterwards. Here you can see some process of developing E2. The top row shows the 3D scanning process, and the bottom row shows the 3D modeling process with a 3D scan as reference. On the left is what was displayed on the phone with augmentations present in the corridor space. Top right are some recordings of participants during the session with no spatial augmentations on the left and with spatial augmentations on the right. A list of questions was prepared for both E1 and E2 and is asked during specific times to the participants during each session. The runtime of the entire experiment was approximately 40 minutes, with each experiment lasting around 20 minutes. Both experiments were qualitative research, with E1 as one-to-one interview and E2 as visual observations. Both experiments utilized the within subject sampling as involved observing behavioral changes in individuals, and 12 participants were observed. In E1, the perception of the participants was altered, but the understanding of the test object did not change according to the augmentations. Participants were able to almost immediately identify the virtuality of the augmented teapots. The sense of presence of the augmentations was weak. And in E2, the perception of the participant was altered and the understanding of the environment changed accordingly. Participants were able to tell the augmentations they saw were virtual, yet all participants showed dramatic changes in behavior when navigating the space with augmentations present. With this in mind, the sense of presence of the spatial augmentations was unclear. Even with the lack of haptic feedback, most participants were confident in the sense of presence of object 2 via video coupling. This suggests that computer graphics in AR would need to reach the level of photorealism, behaving exactly like O2 in all factors to truly allow a strong sense of presence. At this time, this is yet to be achievable due to hardware limitation, and thus proving that virtual materials cannot substitute physical materials. Object augmentations are not capable of changing our understanding of our surroundings, at least not yet. For E2, by comparing the control walkthrough and the test walkthrough, the results show that the altered state of perception of the participants led to change in physical behavior, indicating that their understanding of the space was changed. The virtuality of the augmentations E2 was recognized visually by all participants, yet all of them demonstrated physical behavioral change in navigation through the hallway. This raises an important aspect of AR. It seems not to matter if virtual objects are photorealistic or not, they nonetheless exert physical influence to a degree to the people who perceive them. While both experiments could be further improved, the findings seem to suggest that AR affect our abilities and behaviors in spatial navigation learning more so than in object recognitions and memory. As participants navigate through the hallway in E2, the absence of AR when viewing the space with naked eyes very much reminds me of the story of the Emperor's New Clothes. The augmentations exist only in the participant's perception. For anyone not using AR, the participants maneuvered around fictitious objects in bizarre ways. Thus, the reality in AR suggests not physical existence or substance, but existence in the mental space of the users. In a potential future where AR is deployed en masse, our reality would shift from the physical to the mental, suggesting a host of implications regarding not just the tangible, but also the psychological. Or we might find AR's implementations exciting and in some cases beneficial. We must also understand its consequences in all circumstances. The following section discusses some potential drawbacks of AR in the context of architecture. Here, the objective is not about the rejection of AR, but the encouragement to move forward with clear awareness and open eyes so that we can address these concerns collectively. Learning from the experiments, two types of augmentations can be classified: augmentations that have physical counterparts like an E1 and augmentations that exist with no physical counterpart like an E2. While users may not believe that some of the objects perceived in AR are real, the illusion of the objects may still cause the actors to respond accordingly. Therefore, as an example, people may automatically sit on a virtual chair that has no physical counterpart without thinking, resulting in physical harm, or the opposite, walking into a virtual chair with physical counterpart but assumed to not have any resulting physical harm. When we take the chair scenario and apply it to architectural elements such as doors, windows, steps, balustrades, or even floors and walls, one can imagine that the consequences of misjudgment would be much more serious. In addition, this could be caused not only by human error, but also hardware or software error, raising questions of responsibilities and liabilities in augmented architectural environment. A visually realistic AR experience may not only have physical, but also psychological effects. Psychological realism refers to the psychological sensation that what happens virtually could be happening in reality. AR creates a paradox of visually validated truth simultaneously. A validated truth comprised of the known ground truth, the real world, and a possible virtual truth simultaneously, further challenging separation in the real and virtual and enhancing psychological realism. In view of this, what is believed to be true could be altered by augmentations. At the same time, the realism of the augmentations could be enhanced by the known ground truth. In the context of architecture, assuming that there are significant advances in AR technology, any modifications of the built environment of AR would therefore be difficult or even impossible to distinguish from the real. Although anchoring in the real, the content of AR modifications of architectural spaces is in theory limitless. We must dutifully consider the spatial qualities that might have negative psychological effects on the actor, such as claustrophobia, however unlikely they are. Augmented space is also monitored space. Augmented space is a new kind of physical space that emerges when augmentations are overlaid onto it. While the intentions of virtual overlay may differ from case to case, the result is the same: the creation of a physical space that is data dense, in which every point contains various information that is delivered elsewhere. In the case of the experiment, the AR device must first collect information about its surroundings, then communicate with the AR software in which the augmentation was rendered before displaying the overlay. In this sense, the environments of E1 and E2 in which the augmentations reside became multi-dimensional spaces that are digitized and monitored quietly and invisibly when the AR device is present. The monitor and data collection of the user's surrounding spaces alone could have implications in privacy violation. From a wider perspective, we must also consider the impacts of supporting infrastructure to implement AR, viewing it as a system within a larger ecosystem. A mirror world is essentially a digital twin of the whole world, considering that the foundation of a world in total VR will be based on a mirror world or a similar infrastructure. The question of who has ownership and regulatory authority of the mirror world is crucial. If the mirror world operates similarly to the internet, meaning everyone can share and create AR experiences, these are challenges in how they are challenges in how we can regulate this. For example, how would we shield undesirable experiences from vulnerable populations such as non-adults and patient groups? And if the mirror world is privatized and owned, for example, by Google, then there is the question of jurisdiction and conflict of ownership of the physical space. Either way, we will need to address the complication dynamics of ownership in the built environment. In the case of mass adoption of AR and the deployment of a mirror world, it is highly likely that blockchain remains a platform to provide digital asset ownership, or NFTs. In recent years, we have seen a rise of NFTs, including those dedicated for AR, and in a scenario in mirror world, people will own and exchange virtual objects. Since blockchain consumes energy in the intensive encryption process, the carbon footprint of an NFT is not affected by volume, unlike most physical products. Sustainability concerns will need to be addressed should blockchain remain as energy intensive in the future. As a spatially disruptive technology, AR-related risks are prevalent within and outside of a building's fabrics, but let's also talk about some of its beneficial potential in the built environment. Studies have shown that visual complexity in natural environments, as well as in architectural details, have positive effects on people's moods and well-being. People seem to navigate faster around buildings with simple and monotonous facades, which is compared to the behavior of escaping. While finding interesting and engaging facades more pleasant and thus linger longer, this may be the result of humans being natural-born information processors and thus preferring environments that provide ample amounts of information for us to process. While there are limited studies in what constitutes as positive and visually complex for architectural elements, the exposure of elements of nature have consistently resulted in positive psychological effects in us, such as stress reduction and mood alleviation. In a sense, AR could potentially provide visually richer and beneficial environments, both on the exterior and in interior of a building's fabrics, with the objective to improve mental well-being, especially in urban areas. In addition, if the substitution of physical objects with AR does one day take place, a building could, for example, have a virtual facade that would otherwise cost more money, material, labor to construct, maintain, and deconstruct. In this sense, an augmented architecture can have certain physical elements substituted by augmentations that can even visually transform and translate, creating a performative architecture with little to no cost and time. Theoretically, this consumes less energy with a reduction of material use if blockchains becomes less energy intensive and advances in renewable energy. Although the experiment did show promising results due to opportunistic sampling and hardware limitations, the experiments could be improved. Initially intending to find out about how we react and behave in AR and discussing the implications of AR in architecture. And with the results, the process led to further research questions such as what psychological effects do different levels of visual complexity in architecture have on us. And to conclude, the paper acknowledges that the field of research of AR in architecture is broad, as its development has spanned over decades and is closely relevant to multiple disciplines. With the exponential development AI is experiencing, implications of mass deployment of immersive AR along with the supporting infrastructure that comes with it are significant. The collaboration between architects and all relevant disciplines is crucial in discussing AR's potential and implementing AR architectural designs. The digital is no longer confined to our rectangular screens. AR is already starting to bridge the gap between the digital and the physical. Architects are well equipped with the skill set and the mindset to bring AR beyond entertainment and into the unbuilt environment of our daily lives. At the same time, architects have the responsibility to carefully consider all potential impacts of our physical and virtual designs, both spatially and ethically. Thank you.